You're able to hear me,
Okay.
right?
Yeah, ma'am.
Okay. Okay. You're able to see my screen?
Yeah, ma'am.
Good evening. I welcome you all for the week 4 live interactive session for the course Polymers, Concepts, Properties, Uses and Sustainability. So now let's go on to the session. So uh, let's first recap the contents of lectures of week 4. So week 4 contents were based on polymeric materials of different kinds. So lecture 23 was in continuation with understanding the glass transition, right? Uh, in continuation to the glass transition one, which was covered in week 3. So in the week 4, the concepts of segmental relaxation, where the relaxation time, instantaneous relaxation or no relaxation, right? What does instantaneous relaxation imply? Do you remember instantaneous relaxation? Your relaxation time 0.
Rubber is
It is a completely dissipative material. Whereas when your relaxation time is infinity, there is no relaxation. That means it is a completely perfectly storing material. Okay.
yeah, ma'am.
Okay. Okay, there is one more student joining. Good evening. We have just started with the recap of contents of week 4. Okay. And then there was a discussion on activated process and cooperative process, right? Based on the rate of relaxation, right? So activated process had Arrhenius relationship, whereas cooperative process had a stretched exponential rate, right? And then the free volume theory was discussed, correct? So
Yeah, ma'am.
your free volume gets arrested in below glass transition, right? It becomes fixed, correct? Yeah. And then the William Landau-Ferry equation, Vogel-Fischer equation were all discussed, right? And what is the Arrhenius dependence and how does when there is a WLF different dependence on material property below and above glass transition, and how does a material property differs when there is a Arrhenius dependence and all were discussed. And then what are the other transition other than the glass transition were discussed, right? Right. I need some reply, please, because I don't know whether I'm connected or not. Okay? Because I have some internet issue today. Okay? Yeah. Now let's go on to contents of lecture 24. So lecture 24 was on states in environment, right? So what are the long term and short term impact, overall impact, right? What is the impact on environment were discussed. Biogeochemical cycles were discussed. Do you remember what are the biogeochemical cycles? Someone, what are the biogeochemical cycles? Any of you? Common cycles.
Carbon.
Yes. Yes. Someone is telling. Yeah, you are right. Carbon. What else? Carbon.
Nitrogen.
Yes. Carbon, nitrogen, oxygen, water, sulfur. Right?
Sulfur.
Yes. So these cycles say how how these components get converted to different form and then get back to its original form in nature, right? And then what is the role of polymer in this biogeochemical cycle, whether it is really getting converted back or it is just you know uh, intervening the cycle and then leaving as such, means then sustainability becomes a question, right? So those aspects were discussed. And then nitrogen cycle was discussed, right? Where nitrogen cycle both in nature, what happens, and what due to industrial products and all were discussed, right? and what are the states in environment, the polymers, in water, soil and air, how does it impact, all were discussed in lecture 24, right? Now lecture 25 was on liquid crystalline polymers, right? So the introduction to liquid crystals and what are liquid crystalline polymers, right? What is a free energy change? So these liquid crystalline polymers, they have orientational as well as translational, right? Orientational entropy is actually reduced because of the ordered arrangement, whereas the translation entropy still exists, right? And then liquid crystalline polyesters, PET versus the liquid crystalline polyesters were discussed, where these bulky groups, they act as the mesogens, the rigid uh, parts, correct? And then aramid, the properties of aramid were all discussed. How the specific property of aramid is very high even compared to metals, right? Was was discussed, right? Are you both there? Am I connected?
Yeah, ma'am.
Okay. Next was on introduction to the copolymers, the concepts. What is a homopolymer and what is a copolymer? Sequence distribution. What are the different copolymers that were discussed? What are the different types of
Block.
yeah,
LLDP is a copolymer.
yeah, okay. What is a sequence distribution? Different sequence distribution that was discussed.
It
Some
is. It should be random or most probably it's random.
random copolymers, and then alternate
Graph,
copolymers, block
block, and
copolymers.
gradient
Yes,
statistics.
graft copolymers were all discussed, right? So how polyethylene can be copolymer was brought into, because it is having the CH2 group only, but still it can be a copolymer because not only the ethylene, but even butene, octene, and all, they can involve in the polymerization. So it can have the same CH2 group, but still different monomers are forming the polyethylene, correct? And then silicon polyether was discussed, and then chitosan and chitin was discussed in the copolymers one, right? Next on copolymers 2, the properties, right? How control polymerization for specific copolymer, what is the reactivity ratio, right? What are the, how is it related to the homopolymer, how the free volume, the glass transition and the combined behavior, like the size, the segmental mobility, right? And then the crystallization and all are different, and kind of combined effect in case of a copolymer, in comparison to the homopolymer was discussed. And then the block and graft copolymers were discussed, correct? In fact, in graft copolymers, uh, you know uh, there was a discussion on what material, something interesting was discussed, right? Someone remembers what is that?
This this malleated polyethylene is grafted polyethylene.
Can you repeat?
Malleated polyethylene.
I'm really not sure. I have to just check and get back.
Okay.
Yeah. Right. There was something discussed on graph copolymer. What was discussed on the graph copolymer? Holoxomer was discussed, right? And how it is, in solution to gel form, micelle formation, correct? At 37 degrees. So when it is, stored in deep fridge or fridge or something, it is a solution. And when it is injected into the body, they at body temperature, closer to body temperature, they can form micelles and they get into a gel structure was discussed, right? Right? Do you remember?
Yeah, ma'am.
Yeah. Polaxomer or pluronic, correct? Yeah. And then lecture 28 was on blends, right? How blends can be made, using melt blending and solution blending and reactive blending. Where do you preferably go for solution blending?
Solution
Biopoly.
blending.
Yeah, one by one. Someone started, right? I don't know who started. Nishaj started, right? Just, yeah, yeah, tell me. Where do you preferably go for a solution blending?
Um, I'm not sure because in polymerization itself, for the make of resins like epoxy or phenolic formaldehyde, is solution blending?
No, actually, in case of solution blending, you will have, it is a ternary system. You will have a solvent. Okay, you will have
Okay,
a solvent
one
and
one solvent with two polymer. Okay, I
yes,
got.
yes, in solution blending and in solution blending, one of the key aspects where you go in for solution blending is that you cannot go for a melt blending in certain polymers because the melt temperature, the degradation temperature is closer to your melt temperature. So by the time you're going to melt, the polymer is going to get degraded. So in those kind of materials, you will preferably go for solution blending, and solution blending is common, in biopolymers and all, where water is the major solvent used. Okay. uh, and then there are also reactive blending, right? And what are the different polymeric systems, like polymers and polymer system, polymers, uh, the composites, right? Were all discussed in the miscible, and then what is the miscibility, you will have a rich phase, b rich phase, right? When you have mixtures of a and b, uh, and if it is completely miscible, it will be uniformly distributed. Otherwise you will have a rich phase and a lean phase, right? And what is the polymer solvent miscibility were all discussed in the blends one, on concepts of uh, blends, right? Polymer blends. And then in the final lecture of the week, blends 2. I'm sorry, I've typed it as blends 1. It's blends 2. Okay. The Gibbs free energy due to change due to mixing for an ideal gas, and then Flory-Huggins theory for mixing of polymers were discussed, and then polymer blends and phase separation, the critical temperature, the glass transition temperature of miscible blends, right? Your Flory-Fox equation was discussed, right? Do you remember? You are able to recollect?
Yeah, ma'am.
Okay. So these were all the
Tell me something.
yeah.
Tell me something about the TG of polymer blends.
See, that is where your Flory-Fox equation, comes into picture. Your overall TG, your Flory-Fox equation, do you remember? It is 1 by TG. Will solve a problem similar on similar lines. Your Flory-Fox equation is 1 by TG. That is the TG of the blend is equal to weight fraction of the polymer 1 divided by the TG of polymer 1 plus weight fraction of polymer 2 by TG of polymer 2. Do you remember this equation? This was discussed in the lecture 29. And this similar, concept also goes for, polymer with, your plasticizer or small molecules also. Okay. Shall we proceed?
Okay.
Okay. Yeah.
Yeah.
Okay. Now let's proceed. Or let's get on to the questions. Okay. So the first question for week 4 practice assignment is, the amount of low molecular weight plasticizer with a TG of minus 60 degrees that must be added to nylon 6 to reduce its TG from 50 to 30 degree is dash. So we have to find out what is the amount of the low molecular weight plasticizer that is to be added so that we reduce the glass transition temperature of nylon from 50 to 30 degrees. Okay. Okay, so that above 30 degrees it becomes, more flexible compared to a nylon, 6, where it is above 50 degrees only it becomes flexible. Okay. So this is what is the question. This is a gate 2022 question. So how do you solve this? I think I already discussed while discussing the brief of lectures. So shall we proceed on solving this? Let's go. So what is given? So they're given the glass transition temperature of plasticizer, which is minus 60 degree. Okay. So above minus 60 degrees itself, this plasticizer is very flexible. Correct. And then they have given the glass transition temperature of nylon, which is 50 degrees initially. Now this plasticizer is being added to nylon so that your glass transition is reducing from 50 to 30 degrees. Now we have to find out what is the fraction of plasticizer that is to be added so that this decrease in glass transition temperature of nylon takes place. So what is the weight fraction of plasticizer that is to be added? So you have the Flory-Fox equation, which gives 1 by Tg of the system with nylon and plasticizer, right? The overall system, okay, is equal to weight fraction of plasticizer by glass transition of plasticizer plus weight fraction of the nylon polymer divided by glass transition of nylon polymer. This is again a small molecule, low molecular weight plasticizer that is being added. Okay, so you have only two components, your plasticizer and nylon. So again your weight fraction of nylon can be expressed as 1 minus weight fraction of plasticizer, correct? That is what I have done it here, right? You are able to figure out that, right? Because it's only two components. So if you know the weight fraction of one, the weight fraction of other will be 1 minus the weight fraction of the first one, right? So that is what I have done in the weight fraction of nylon. And then you just have to substitute. Here again you have to take Tg. Tg they have given in degree Celsius. You have to convert it into Kelvin. Okay. So it will be 1 by 30 plus 273, right? And similarly minus 60 plus 273, 50 plus 273, right? So 1 by 303 is equal to weight fraction of plasticizer by 213 plus 1 minus weight fraction of plasticizer by 323. So that will end up with a weight fraction of the plasticizer to be 0.1278, which is nothing but 12.78%. So if you add 12.78%, approximately 13% of the plasticizer, the glass transition temperature of the nylon gets reduced from 50 to 30 degrees. Okay? You're able to understand?
Yeah, I got it. Because weight fraction, we have to take it as one as the total weight fraction, no?
Yes, yes, yes. Yes.
Okay.
Yeah. And since it is just only two components, so if you know the weight fraction of plasticizer, then you can know the weight fraction of nylon also, because it's just 1 minus, right?
Suppose if the weight fraction is given in a separate numeric, then we have to go with that value.
I didn't understand. In separate numeric in the sense?
Suppose here it is nylon, the weight fraction is not given. If suppose they are giving the weight fraction, we have to directly.
You can directly find out. You already have the weight fraction information. So the weight fraction of plasticizer, you can just directly find out by just subtracting it from 1. Correct? Because
So,
only two components are there.
so this should be a fractional term in a point terms. If
Yes,
they are
yes.
given a percentage, if they are given percentage, we have to convert into the fraction.
Yes, yes, yes. You're
Okay.
perfectly right. Okay? So you're perfectly right. Now, I'll ask you this question in a different form. Say, for example, they have given a plasticizer is being added in this case. Okay? And they have given the glass transition temperature of, uh, you know, you know, nylon and plasticizer, everything. Now, let's also look into this question in another form. Say, for example, they have given two different materials. And for example, one plasticizer and nylon and nitrile rubber. Okay. And they say that, uh, you know, the you know for example, what is the weight fraction of the plasticizer? Now we have to find out the weight fraction of nylon. Okay, and they've given the weight fraction of plasticizer. They have given the weight fraction of nylon. They have given the TG of overall component. Okay, the combination of plasticizer and nylon they have given. Okay, imagine they have given all these details regarding the nylon and plasticizer combination. Now they ask, find out what will be the amount of nitrile rubber in place of plasticizer you have to add, so that the glass transition temperature reduces to the same extent. Then how will you find? Imagine you don't have the information on glass transition temperature of nylon, pure nylon. Then how will you find? Okay, you're able to understand the question?
Yeah, I got the question. I got.
Okay, they have given three components, materials. One is some plasticizer, the other is the polymer nylon, and another is nitrile rubber. Okay,
Okay.
and what they are giving is that in case of the plasticizer nylon system, they give what is the overall TG when both are together, and then what is the weight fraction of nylon, what is the weight fraction of plasticizer, and the TG of plasticizer also they give. They don't give what is the TG of nylon. Okay, now they ask a question, what will be the weight fraction of rubber, nitrile rubber, say for example, or some other polymer that is to be added in place of plasticizer along with nylon. So you're replacing the plasticizer with some other material along with nylon to reduce the TG to the same extent. So how do you find the weight fraction of that other material that is to be added? Because both the material, the same amount of, for example, plasticizer here you use 12.78%. The same 12.78% will not and cannot be used for a different material. Correct? So how do you do?
Correct.
So how do you go about that?
So here the problem is that in nitrile rubber they didn't give a weight fraction as well as TG. So both is missing
No,
from nylon.
in nitrile rubber they have given the TG, but for nylon they have not given the TG. So what happens in that
Okay.
case?
Okay. Okay. So
How,
so first we had to find out the TG of nylon.
yes, how do you find?
Uh, because weight fraction is given and total TG is given and total
Yes,
TG of plasticizer is there.
yes,
So from this equation we can find out the TG of nylon.
yes, correct.
First, first we have to find out the this TG of
Nylon
nylon. Okay,
and
then we take the plasticizer out, then kept this nitrile rubber.
yes, yes, and
Okay,
then the TG of
so
nitrile rubber, and then you
yeah,
replace the
so
TG of nitrile rubber, and in the same
yeah,
expression, if you substitute,
yeah,
you will end up what will
weight
be the
fraction,
weight fraction of
weight
nitrile
fraction
rubber.
will get. Yeah,
Yes, yes.
this
This
one.
was again actually a question, a gate question which was asked, I think in 2012 or 2013. They have given it in a indirect way. It was like a two subdivision question.
Yeah, okay, got
Okay.
it.
Yeah.
But the thing is that we have to take care of only the TG should be taken as in Kelvin. That
Yes,
is the
yes,
important.
yes, yes, yes. Always, we have to see, whenever some equation is given, you have to, find out in that equation any parameter, whether it is temperature or pressure, whatever it is, what unit, in what unit that particular equation was, defined for. Because in certain cases, some equations will be defined directly in degree centigrade. Okay, but in certain equations it needs Kelvin, or some certain equations it may need in Fahrenheit. So you have to understand in which units this equation was defined. So you have to understand that also. So units is important. In some cases, for example, if you are having some ratio of temperature directly, and the original equation wasn't Kelvin, right? In those equations, you need not necessarily convert degree centigrade to Kelvin because the difference will be the same, right?
Yeah.
So
One
you
more
can,
thing.
yeah.
See, how many assignment we are getting total? Because last assignment I forgot the date and I missed.
Okay. I'm
I
really,
actually prepared, but I missed.
oh, okay. I'm really not sure. I think last year when we were discussing, it was 8 out of 12 you have to, but I don't know whether they have changed this time or not. Maybe you can just, check in the course page. They would have given those, requirements of how many assignments you have to complete in order to, register for exam or, in order to attend exam. There will be some requirement they would have mentioned.
And in assignment there, I have another concern. If they are asking such problems, okay, suppose this is the problem, the right now in the screen the same problem, okay,
Okay.
and if we are this 0.1278, it is a perfect integer. If we put this perfect integer only, the answer will be right. Suppose somebody is calculating and they are putting 0.128 instead of this one.
Okay.
So whether the software will take it directly or somebody is manually this taking, this is my another concern.
I guess it is by software because I saw a question in the forum also. Someone has written, but always check in the, question, say for example, here it is say rounded off to nearest integer also it is saying. So that means you can just directly say as 13%.
Yeah, that's the problem, because
Yes,
if
yes.
software
So
is
you have
taking
to,
this direct.
yeah, yeah. You have to, preferably you just see if these kind of, additional information is given in the question, like round off to, two decimal places or round off to one decimal place or round off to near integer. Check that. But by mistake you give, I think there is a question raised in the forum. One of the student they have asked, for some, I think unit cell calculation or something. He has mentioned it as 0.0933, whereas the given answer was 0.093, and he was marked
Yeah,
wrong or
correct.
something. I don't
Yeah,
know. We
yeah,
have
this
to
is
check.
this is the problem.
Probably the NPTEL team has to check. How it is getting evaluated, so that these issues can be sorted. Probably they will be answering that query, I guess.
Yeah, because there is no such answers. Like answer is also giving in a different pattern. No?
Okay,
If
but
it is approximate, it's okay.
yeah, but generally, just see if these kind of information is given, round off to the nearest integer or round off to two decimal place. If they have given, make sure that you just round off to that requirement so that you will not
Here
fall
itself,
into those discrepancies. But by
round
mistake,
off. Yeah, I understand. Round off to the nearest integer, it itself, it is not making any sense here.
nearest integer means instead of you have to remove all these decimal places, you will end up with around 13% instead of 12.78%. You will say it as 13%.
Yeah.
Okay, just see those, if there is a specific requirement that is being given, and just stay aligned to that requirement. But otherwise also we'll just check it out how it is getting evaluated. Okay.
Yeah.
Okay. Okay. Now can we proceed to the next question? Polyvinyl chloride has a higher glass transition temperature than polypropylene due to the presence of dash. What makes polyvinyl chloride have a higher glass transition compared to polypropylene? Is it a bulky side group, or is it due to polar interaction, or is it due to restriction of bond rotation, or is it due to non-polar interaction? This
With
is
polar
again
interaction.
okay. So what about the other person, Kirtivasan? What do you feel?
Polar interaction due to chlorine.
Okay, okay, okay. Yes, you're all right. It is due to polar interaction. So as you all said, so this is having chlorine. So this will have kind of polar interaction compared to polypropylene where you have just a methyl group here, right? So that is the reason. So this is again a GATE 2017 question. Okay. Now let's proceed. So, so in terms of value, the PVC is having a glass transition of nearly 80, whereas polypropylene atactic is nearly minus 20. Okay. Now let's proceed to the next question. Butyl rubber is a copolymer of, is it a copolymer of isobutylene and butadiene, or is it a copolymer of butadiene and 1-butene, or is it a copolymer of isobutylene and isoprene, or is it isoprene and 1-butene? It is a copolymer of which of the two? Which two monomers form the butyl rubber copolymer? Someone A. Okay, someone is saying it is. I think Kirtivasani is saying isobutylene and butadiene. What about others? What do you say? Is it isobutylene and butadiene, or is it something else? Any
I
option?
think it is A.
A. Okay. Okay, two of you are saying A.
Because,
What about the
yeah,
third
my
person?
concern isoprene is not there. That's my
Okay, wait.
idea.
Okay, let's see. Let's see what is the answer. Let's see what the other person answers also. Any option, Manshi, you want to give?
I will go with a C option, and isobutylene and isoprene is the
I
right answer.
Okay. Yeah, now let's go in for the right answer. It is actually option C. It is isobutylene and isoprene. So you have the isobutylene structure, isoprene, and this is how the isobutylene or butyl rubber looks. Okay. It's a combination of isobutylene and isoprene. Okay. Hope you.
Okay, it's a direct question. I don't know. This is the thing.
Okay.
Okay, I
That's okay.
forgot.
That's okay. We are all learning. Okay. We are all learning. Okay. Now let's proceed to next. Thermodynamically, two polymers with enthalpy of mixing delta H and entropy of mixing delta S forms a miscible blend at a temperature T when does two polymers form a miscible blend? So, is it when delta H by delta S is equal to 0.5 of T, or is it delta H by delta S is equal to T, or is it delta H by delta S equal to 1.5 times of T, or is it delta H by delta S is equal to 2 times of T? Under which conditions two polymers form a miscible blend? This is again a GATE question, GATE 2014 question. Any thoughts?
No idea. I will go with C.
C. Okay, someone is saying C. Anyone else wants to give a try? What about Manshi and Kirtivasan? You want to give a try, or let's proceed with how to solve this?
Let's proceed.
C. Okay. Okay, why do you think C? Or is it just you are just giving a guess?
I'm saying let's proceed further. I have no idea about it.
Okay, 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 okay. Now let's see what is the answer. So to form miscible blends, how do you start with? You start with your free energy of mixing should be change in free energy of mixing delta G of mixing should be less than 0. Okay, that is what is discussed right in this particular slide where the flow reagents theory was discussed. Okay, so delta G of mixing should be 0. So if you just thermodynamically express delta G of mixing, it is nothing but Enthalpy of mixing minus T delta S of mixing should be less than 0, right? Now just realigning that. So enthalpy of mixing should be less than T delta S of mixing. So delta H of mixing by delta S of mixing, enthalpy by entropy, delta H by delta S should be less than T, right? So among the given option, only option A, if you see, it satisfies the condition that delta H of mixing by delta S of mixing is less than T, correct? It is 0.5 of T, it says. Others are either T or 1.5 times of T or 2 times of T. So the condition that satisfies that, the two systems, two polymer forms of miscible blend is here among the option, it is delta H by delta S is equal to 0.5 of T. And in general, it should be less than T. Okay? Hope you are all clear. Are you all clear?
Yes, ma'am.
Okay. I just need a reply of yes or no because I'm having some internet issue. So I just want to know when I go to the presentation mode, I may not be able to see whether you are all there or not, or am I connected or not. So for that purpose, I need yes or no, or you're not able to understand something I need. Okay, or please proceed something. Okay, yeah. Now let's go on to next question. Monomers A and B form block copolymers when reactivity, the rate of reaction Ra is equal to Rb is equal to 0, or Ra equal to Rb equal to 1, or Ra is greater than 1, Rb is greater than 1, or Ra is less than 1, Rb is less than 1. Under which condition you can form block copolymers? This was again discussed in reactivity in copolymers, I think copolymers 2.
Uh, let me discuss this one. Ra is equal to Rb is equal to 0 means there is no reactivity. So let me Ra is equal to Rb is equal to 1 means it will form, according to me, it's a random polymer.
Okay.
So it should be greater than 1. So I'll go with the C.
Okay. What about others? What do you think? Are you are you also agreeing with Nishet's answer?
Yeah, ma'am. It should be greater than unity.
Yes. Okay. So all of you are right. So when Ra is greater than 1, your Kaa by Kab, that is the monomer will preferentially get attached to another monomer A. And similarly, when Rb is greater than 1, monomer B will give preference to monomer B only. So this leads to blocks of A and blocks of B. So this leads to blocks of A and blocks of B forming block copolymer. So you will form something like AAA, BBB, AAA, BBB. Okay. So you are right. So this is how the block copolymer is formed. So the reaction rate, should be greater than 1 for both polymer A and polymer B. So that your rate constants Ka is higher than Kab. That is the affinity of A to A is more than A to B. And similarly for B also, B to B is more than B to A. Okay? Yes, so you were right. Now let's proceed to next question. A linear amorphous polymer has a glass transition of 10 degrees. At 28 degrees centigrade, it has a viscosity of 4 into 10 power 8 poise. The viscosity of the polymer at its glass transition is dash into 10 power 13 poise. This is again a gate question. So they are given glass transition temperature of some amorphous polymer, and then they've given the viscosity at a particular temperature. Now we have to find out the viscosity at glass transition temperature. So what should we use? How should we go about? Any thoughts?
It's practical. I don't know whether it is correct. I will go with a thumb rule. it should be 1 into 10 raised to 8. Oh, no, 1. Something.
How do you get into that?
Oh, viscosity. This viscosity is increasing, no?
Okay.
No, there's a thumb rule. I don't know whether it is correct or not in this case, because every 10-degree temperature rise, the property should be doubled. That is the thumb rule. So,
Okay. Now, anyway, so what about Kirtivasan and Manshi? You want to give a try? How to proceed with this?
You please go on.
Yeah, you were saying something?
Ma'am, you can go with that. I
Okay,
have no
oh,
idea.
okay. So, given the glass transition temperature of the polymer is 10 degrees. They have also given viscosity eta T or eta 28 degrees as 4 into 10 power 8 poise. Now they have asked what will be the viscosity at glass transition temperature, which is nothing but what is the viscosity at 10 degrees centigrade. Right? We have to go in for this WLF equation. Okay, this time temperature superposition concept. This was actually discussed, right, in I think in glass transition. Yeah, glass transition lecture it was discussed. So log of eta by eta g is equal to minus of C1 into T minus Tg by T minus of Tg minus C2. Okay, your WLF equation was discussed. And then the universal approximation for C1, the constants are 17.44 and C2 is 51.6. Generally, C2 is approximately 50. Okay. And then you have all other terms, right? Now you have what is eta at T, you have what is C1, you have what is T. T is 28 degrees and Tg is 10 degrees, right? Now if you just substitute all the parameters, you can find out what will be the viscosity of the polymer at glass transition. So someone can calculate and tell me what is the viscosity at glass transition? Just the mathematics, you have all other terms. And one more thing you can just note it here is that I have just directly used the temperature in degrees centigrade. I have not converted to Kelvin because in the numerator also there is a temperature difference. In denominator also there is a temperature difference. So in Kelvin and degrees centigrade the difference will be the same because you just have to add plus 273 for all the temperature components. So either if you are going to take 28 minus 10 or 28 plus 273 minus of 10 plus 273, it is going to be the same. Similarly in the denominator. But only in the numerator you have the difference. Whereas, yeah, even in that case, if the denominator is going to have some temperature in Kelvin also, the difference is going to be the same. Right? So this is where, you need not really go in for a conversion from degree centigrade to Kelvin. So someone is trying to do the calculation, mathematics. What is the answer for this? You have log of 4 into 10 power 8 by viscosity at glass transition is equal to minus of 17.44 into 28 minus 10 by 28 minus of 10 minus 51.6. What is the value? Someone is making the calculation.
um, log, log, log. Here is. How we'll go with? I don't know because we have to go with the exponential or direct.
When you take log to the other side, it should be 10 power of this minus of 17.44 into 28 minus 10 by 28 minus of 10 minus 51.6. Only when you have natural logarithm, if it goes to other side, it becomes e power, exponential. Here it becomes 10 power because it is log to the base, yeah, it is log to the base 10.
Mm. It's difficult because it's long back all this max.
Okay, what about Kirti Vasan and Manshi? Are you giving it a try to calculate it?
Yeah.
No, my question is that we have to take log a by b is equal to log a minus log b, like that. We have to go.
Not necessarily required. First, you finish off the mathematics of this portion, and
This
then
portion I got around 4.51 minus 4.51. I don't know
yes,
whether it is correct or not.
okay, and then you just have to bring, when you bring this log to the other side, it becomes 10 power of minus 4.5.
10 bar of
Mi-
okay minus 4.5.
10 to the 10 raised to minus 4.5.
Yeah, okay. So 4 into 10 raised to 8 divided by 10 raised to 4.5. So this is 4 into 10 raised to 8 plus 4.5. So 4 into 10 raised to 13. So 4 into 10 raised to 13. Again, we are getting the same answer.
Is it 4 into 10 raised to 13? What about others? Yeah, Manshi is trying to say something.
4 into 10 raised to 8 divided by 2 plus transition is equal to this one 4. So yeah, 4 to 10 raised to 10 raised to 5.
Are you able to get what is the viscosity? Kirtivasan, you are able to find out?
No.
Okay. Anyway, I'll just show you the answer. So this is how it goes.
Yeah.
Your answer will be 1.295 into 10 power 13. So what happens is that 10 raised to the power of minus 4.5, you will get something as 0.0000. That is 4 zeros followed by 308. Okay. So 4 into 10 power 8 divided by point 4 zeros 308. That will end up in uh, you know uh, into 10 power 8. Okay, 4 into 10 power 8 divided by point 4 zeros into 308. That will, you will end up in 1.295 into 10 power 13. Okay,
Mm.
you got it?
Not so easily. I will do it later. Okay, that's better.
Give it a try.
Yeah.
Yeah. Okay, now let's proceed to the next question. The size of a coiled polymer chain in a dilute solution is Rg in a good solvent Ri in an ideal solvent and Rp in a poor solvent. Select the correct ordering of sizes. So is it Rg greater than Ri greater than Rp, or Rg less than Ri less than Rp, or is it Rp greater than Rg greater than Ri, or is it Rp less than Rg less than Ri? So which of these is correct? Under which condition? Under which condition you will have the maximum size for the polymer chain, and in which you will have the minimum size? This is again a GATE 2021 question.
According to me, it's D.
D. So the radius in a poor solvent, or the size in the poor solvent, will be less than the size in the good solvent, will be less than the size in the ideal solvent, is it? Okay, you have given option D. What about others? What do you feel? In which solvent it will have the maximum size? Any thoughts? Kittivasan, any thoughts? Or shall I proceed with the answer?
Just proceed.
Okay, let's proceed. It is actually option A. In good solvent, it will have maximum size followed by ideal solvent, and then in poor solvent. Why is this one? So in good solvent, there will be a solvation of macromolecule. It will be of more of an expanded chain. Okay, in good solvent, right? And then in ideal solvent, it behaves as if there is nothing around. And in a bad solvent, it will be collapsed chain. Obviously, in collapsed chain, it will have the least size, and you can see the relationship of the radius of gyration with molecular weight. So it is in a expanded chain, or in a good solvent, it is Rg is nearly m raised to zero point 0.6, whereas in ideal it is m raised to zero point 0.5, and collapsed chain or in a poor solvent, uh, where the macromolecules are interaction is more than macromolecule and solvent interaction, then Rg is nearly m raised to 0.33. Okay, you all got it?
So this is based on the entropy concept.
This is based on your solvent and polymer interaction concept, because when you're if it is in a good solvent, obviously there will be more of a solvent and polymer interaction, so it will tend to expand itself, right?
Yeah,
The
that I got the
intermolecular,
point, but ideal solvent means there is no such solvent, or just theoretical.
is theoretical. Your ideal
Yeah.
chain
So
concept
ideal.
itself is more of a theoretical concept, right? There
Yeah.
there
In
will
in in,
definitely
in
be interactions, right? It is very similar to your ideal gas concept, correct?
yeah. So
Yeah.
the ideal condition, the coiled polymer will make a coiled structure again,
Yes, it will be
to
make a
reduce the
coiled
entropy.
structure, and it also behaves that as if nothing is there around it.
Yeah, yeah,
Okay.
I understood,
Whereas,
because it will go to the minimum entropy level.
yeah, whereas in collapsed
Yeah,
chain, or if it is in a poor solvent, no, there will be the polymer
it,
polymer interaction will be much more. So it will form much more of a collapsed shape, and that is why the size will be the least. Okay.
yeah, that makes sense.
Yeah. Okay. Okay, now let's proceed to the next question. Enthalpy of crystallization of liquid crystalline polymer is lower compared to semi-crystalline polymer. Okay, why is it so? Why do you think it is that way? This was again discussed in the liquid crystalline polymers lecture. Do you want to give a try, or I'll just proceed? There is silence. So, for,
Proceed better because
okay,
I
okay,
don't.
okay. So, why is it so? Because in case of liquid crystalline polymer, it is only there is an orientation order, but you can still have translation and entropy present. Okay, so if you look into the structure, so these mesogens, they can shift, they can translate between the positions. Only thing is that the order will be maintained, but the positions can be transferred. So uh, that is the main reason. Whereas when you look into the semi-crystalline polymers, this kind of translational motion is not possible in the ordered places or in the lamella. Okay, that is the reason why yeah, their enthalpy or the heat requirement for forming a liquid crystalline polymer is much more. That is why you have a liquid like plus a crystalline behavior, solid like behavior. Okay, hope you all got it.
Not really, but the translational, uh, I don't get the idea. Translation exactly.
What happens in translation motion? See, you're able to see my pointer. So
Yeah.
this group, this
This
mesogen.
is this white spot is the bulky groups.
Yes, these are the bulky groups or the mesogens or the rigid groups. Okay, these
Okay.
rigid groups can still move about or shift places within this order alignment. So, for example, this point can move from this to this, and this can move back from this to this. So, the order is still maintained, but there is a movement
But
also, right?
physical movement. It's a
Yes,
physical
yes,
movement.
yes. There. So this say for example, imagine this as one and this as two, right? The arrows
So it's
marked
not
out.
it's not linked with the this main chain in
No,
physical bonding. No.
see, it will have, uh, see, this is all in the part of the chain, but what happens is that these are all groups with the, other polymeric, linkages and all. But these groups can just shift places. Okay. These are all complete one, polymer. They are all, pieces of polymer. So these can shift between places. Okay. This is
Because
translational.
I don't. Yeah, because I don't have much idea about liquid crystalline volume. I heard about this liquid crystalline. I
Okay,
didn't
okay.
go well with the liquid crystalline. Is this liquid crystalline polymers are liquid or solid?
That is where, so they are having a liquid like behavior because of high translational motion, whereas they have some specific ordered alignment. If you can see, they have some definite alignment. You can see the cylinders are arranged in some definite patterns here. Similarly, the discs are arranged in definite patterns here. So that makes it
Okay.
crystalline. So when you have a definite ordering, it is a crystalline, whereas still they
So
are able
basically,
to move.
it's a liquid kind of material processing a property of crystallinity.
Yes, 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 yes,
Yeah.
yes. If you go through that lecture, no, you'll get into better insights.
Okay, got it.
Okay. Yeah. Now let's go on to next question. Plastics have density similar to water. Identify if the statement is true.
No.
Why do you say so?
So plastic will, most of the plastic will float.
Okay.
So float in water. So the density is lesser.
Okay.
No, 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 no.
I mean,
It's in the
I'm
opposite.
not saying it is same. It is similar.
Mm,
Similar and same are different.
almost similar. I can say almost similar because the density is somewhere near to one.
Yes. So it is actually similar. The statement is true. And that is the reason why, in water bodies and all, when you throw plastics, so it gets carried away because of the similar density, it gets carried away over long, places. You throw the plastic in some place, but, it passes through the water body and it gets, it ends up in some other place. So that becomes again, kind of a sustainability and, pollution issue. It gets accumulated and it gets it starts floating and moving to some other place in the stream of water. Okay.
Correct.
Yeah. Okay. So overall impact of polymers is assessed based on, so this was on, the sustainability, or states of polymers and sustainability, uh, that lecture. If you had gone through that lecture, you will be able to.
Impact uh, based on recovery.
Is it only on recovery? Let's see the answer. It is actually based on the life cycle assessment and then biogeochemical cycle. Okay, life cycle assessment means it is from the, preparation till, if you are able to completely biodegrade into, or if it goes into the nature completely, breaking into, the basic elements. So that life cycle assessment, you know or is it, getting dumped and, it is causing, pollution issue or all those things, or how you are recycling, and all those aspects come into life cycle assessment. And how is it involving in biogeochemical cycle, whether it is just participating and coming back, or is it actually getting converted, like, obviously polymers have carbon, so the carbon, there's a carbon biogeochemical cycle. So is it getting converted back to the carbon, uh, or, is it somewhere, going and then coming back, in the cycle? So these are all assessed. And then ecosystem analysis, how it is affecting the ecosystem. So everything, comes into consideration when you think of the overall impact of polymers and their sustainability. Okay.
Yeah. Now nowadays people are looking for different R. That is the basic thing. Recyclability, recovery, regeneration. All they are developing different R
Yes.
R R terms.
Yes. 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 And also, no, when you're recycling, also, no, how does, the material property during its, functioning, and after throwing it off, also, how it is really behaving. So a lot of pictures, concepts come into picture. Okay. uh, LCP at high temperature behave totally like solid. Hmm, high temperature, should it behave totally like solid? Really not sure. Maybe I'll just check and get back to you, Kirtivasan. I'll just note down the
Okay, ma'am.
question. Should it behave totally solid like, or should it behave totally liquid like? At high temperature, there's lot of, uh, because even the, inorganic materials, no, at very high temperature they become melts, right? There itself,
Yeah, ma'am.
even for inorganic materials, it becomes melts, and, it is liquid behavior. So how can you know liquid crystalline polymers behave totally solid like at high temperatures? Ah, it's very
Actually, in lectures, there was a line. However, solid-like responses obtained at very high temperatures due to liquid crystalline order.
I'll just get back to that. What is that actually? It does
Okay.
maybe the professor is you have to see the sequence of statements, not just a single statement. It would be in the previous line and the next line. You have to understand why this term particularly came in. Okay, I'll just check
Okay.
and get back. Okay, I'll just check, and you can also go through the lecture again and then find out. Okay,
Yeah.
yeah. Next question. Changes in properties due to subsegmental relaxation are dash compared to that of changes due to class transition. Is it higher, lower, or same level, or none of the above? The property changes due to subsegmental relaxation are dash compared to that of property changes due to class transition. What do you think? Will the property difference be high compared to a change after glass transition, or will it be low, or will it be of same order or same level as that of changes due to glass transition?
Lower.
Okay, what about Kirtivasan? What do you feel?
Some subsegmental relaxation. I feel it's lower compared to TG.
Yes, both of you are right. Yes, the changes in properties due to subsegmental relaxations are lower compared to that of changes due to class transition. So the changes due to class transition will be much higher compared to your subsegmental. So you could see, here your specific volume changes. So the specific volume change in this region, it is very high before and after class transition compared to your subsegmental change. So the slope actually it is lesser here. That means the property changes comparatively it is decreasing compared to your glass transition change, right? So as you all said, it is lower compared to your glass changes due to glass transition. Okay, now let's go on to next question. Hydrophobic chitin is converted to hydrophilic chitosan by replacement of hydroxyl group to acetylamine group, or acetylamine group to hydroxyl group, or acetylamine group to amine group, or amine group to acetylamine group. Which change happens?
No idea. I don't have this.
Okay, the answer is acetylamine group gets converted to amine group. So if you just look into the structure of chitin, this is the structure of chitin. So it is having NHCOCH3. So this gets converted to NH2 group, amine group, and this forms chitosan. Okay, this is what happens for chitin to chitosan conversion. Okay, now let's go on to next. Silicon polyether copolymers are widely used as, what is the major use? They are used in various applications because of one, kind of a overall behavior.
There are two properties basically for silicon polyether. One is high temperature property and biocompatibility. That is the two things, what I believe.
Okay, okay, it's saying that.
Surfactants.
Yes, yes, it is because of the surfactant nature, it is used in wide range of applications. So it can be used as an emulsifier. So wide range of applications can be, applied. In oil industries, it can be used since it is because of the surfactant nature. Wettability can be exploited because of the surfactant nature. Because your silicone, if you look into this silicone, it is hydrophobic in nature, whereas polyethylene oxide, this ethylene oxide group is hydrophilic in nature. So hydrophobic and hydrophilic together they behave like a surfactant. Okay, that is the major reason why it is widely used in different application wherever kind of surfactant kind of behavior is necessary. Okay, now let's go on to the next question. In case of random copolymer containing monomer M1 and M2, where M1 has the ability to crystallize when it polymerizes alone. The crystallization of M1 in copolymer is possible under which condition M1 can polymerize in a copolymer of M1 and M2 in a random copolymer. This was again discussed in class. So, shall I proceed with the answer or you have any thoughts? You want to give a try?
I have no idea because random. I don't think so. I don't have any idea.
Okay.
And block polymer, okay, but
Yeah.
random.
So as I said, so random copolymers again, when you have to crystallize, if one of the polymer is able to crystallize, when it crystallize, when it polymerizes alone, but in a copolymer, the crystallization becomes difficult because you will have M1 and M2 randomly placed in a random copolymer especially. So what you have to bring in to have a crystallization of M1 in a random copolymer is that when you're cooling the random copolymer from a mill state, there should be a demixing of M1 and M2 and then exclusion of M2 from lamella, so that in those places where M2 is excluded and M1 is there, there is a possibility that M1 starts crystallizing in that zone. Okay, this is the condition where you can make crystallization possible in a random copolymer. Okay. Now next question. Miscibility in block copolymer is similar to that of polymer blends, where in the case of mentioned copolymer, domains are combined with dash, where the domains are dependent on dash, the key determinant of microstructure of block copolymer. So block copolymer and your polymer blends, they are very similar. They'll have domains. Whereas the key difference between block copolymer and polymer blends is one particular thing, and these domains are also dependent in the case of block polymers on a particular aspects, which is a key determinant of the microstructure of block copolymer. What is it? This is again discussed in lecture. In the slide you will not find it, but when the professor narrates it, he would explain that. So you have to just make note of those points. So shall I proceed with the answer?
Yes.
Yeah. So it is actually the difference between a block copolymer and polymer blends is that in block polymers there is a covalent bond between the domains. Block copolymer again you will have AAA, BBB. So domain of A, domain of B. But this domain of A and domain of B are connected by covalent bonds. And one of the key features of these block copolymers is their block length. Then that determines the microstructure of block copolymer. How it will be, how the microstructure is defined. That is the answer for this. Okay. Now next question. For a polymeric system of A and B having LCST, as we increase the temperature for the same volume fractions of A and B, the polymer system LCST is lower critical solution temperature. Hope you remember. So for the same volume fraction, if we increase the temperature, the polymer system becomes miscible from partially miscible system, or it becomes partially miscible from miscible system, or becomes partially or is it partially miscible in both the cases, or is it miscible in both the cases. So you're increasing the temperature from a lower critical solution temperature, okay, for a polymeric system without disturbing the volume fractions of A and B. So what happens if you increase the temperature in that line? Whether it will become from a miscible system to a partially miscible system, or it will become a partially miscible system from a miscible system, or it will become a partially miscible system in both the, or is it a partially miscible system in both the cases, or is it a miscible system in both the cases? What is the scenario?
No idea.
Okay, it actually becomes partially miscible from a miscible system. So if you just look into this, so this is the temperature versus your volume fraction. So below your lower critical solution temperature, the system is completely miscible. So where for a particular, say for example, a volume fraction of 0.5, if you start moving from this lower critical solution temperature and you keep on increasing the temperature, it becomes a partially miscible system. From a miscible system to partially miscible system, it gets converted. Whereas in the upper critical solution temperature, if you bring down the temperature from from a higher temperature to lower temperature below the upper critical solution temperature, it becomes partially miscible. Okay. So for LCST, below the LCST, it is completely miscible. For UCST, above the UCST, it is completely miscible system. Okay. You're able to get it? Hello, are you
Yeah,
all?
from this graph. Yeah,
Yeah, ma'am.
from this graph it is.
Okay, okay, okay. So that's it with the questions. I will also share some questions that were posted in the forum during the last, July November 2022 sessions for the same week 4 content. So there was a question asking why silicone is commonly used as a coating agent, whereas silicone is an elastomer like rubber. What makes silicone restrict its applications only in limited areas? Why not as tire? And what is the reason and how to make silicone suitable for various applications? This was the question posted by one of the students called Sweta. So the answer given by the professor for this is that, so applications of material is not based on the class of behavior alone. So just because silicone is a rubber-like material, it does not mean that it can replace rubber-like materials in all applications. Okay, so several factors comes into picture. A material can be based on combination of several properties, and one of the important factors is cost. And silicones are very expensive materials, and that this is the reason, they are not replaced in tires or anything, or not completely wherever you have rubber, you are not replacing it with a silicone. Okay, this was one of the questions. One more question was, why not alternating copolymer could be a homopolymer as it contains same repeating unit throughout the chain. This was one question posted by Uday Kumar of last session. So what the answer is that, again, alternating copolymer is PQ, PQ, PQ. This is what is a alternating copolymer. So he was asking, since it is only PQ, PQ, that means why can't it be called as a homopolymer? So that was his question. So the answer for that is that, so PQ is an alternating copolymer. So the homopolymer will be of P will be PPPP. Okay, that can be formed from monomer P, and similarly QQQ from monomer Q with repeat units of P and Q respectively. Right? So a polymer with the so this can P can form a homopolymer P separately, PPP separately, and Q also can form a polymer separately. So obviously the repeat unit for PQ is called as a copolymer of P and Q. Okay. The next question was whether orientation of fibers.
Uh,
Yeah.
One second, one second. In this question number 2,
Mhm.
this is an interesting question. I like it.
Okay. Okay.
So the thing is that here PPPP is forming a material with P as the monomer, okay,
Yes.
and QQ is forming as Q as the monomer.
Yes.
Okay. Now the alternating copolymer, it is PQ PQ PQ. Agreed.
Yes.
So as a generally, if anybody looking to this system, it is just like it seems like a uh, homopolymer PQ PQ PQ. Okay. So the thing is that my thing is that here, if anybody can make a monomer PQ,
Hmm.
and that monomer is possible to make as a PQ polymer, then it is a homopolymer. But the thing is that PQ monomer formation is not possible.
That is one. That can be one case. See, you can also think of these condensation polymers like polyethylene terephthalate, where maybe your ethylene glycol and terephthalic acid reacts. So ethylene glycol again, you can form a polymer with ethylene glycol. That is what is polyethylene oxide or PEG, polyethylene glycol. Whereas terephthalic acid, I don't think you can form a polymer of its own. Correct. So,
Yeah, correct.
so when you're considering this alternating copolymer, as you said, PQ cannot be if PQ is able to form a monomer separately, then
Then it is possible,
it
but it's
becomes a
normal.
homopolymer. But if that
Yeah,
doesn't form a monomer separately, then it's not possible. Yeah.
it's not possible. Yeah,
Yes.
it's a good question. Yeah, I like.
Yes. Yes. So next question is whether orientation of fibers or any particles into polymeric system is controllable. And if so, how is the question. This was again posted by one of the students called Shweta. So the answer was orientation is affected by flow and deformation during processing. So during shearing, a rod-like object can be oriented in flow direction. So this is what happens, especially when you have these fibers and all, obviously during processing, if you can orient due to processing, due to the flow and deformation, obviously it can be oriented in particular way. In many cases, that actually helps in orientation of, for example, if you have some polymer with cellulose fibrils during processing, when you apply a shear during processing, these cellulose fibers can orient and they can orient in particular direction, and that can cause property anisotropy, which is very useful, and it helps in building up the material behavior. Okay, so this was one more question. That these are all the questions that were asked in the week 4, and that were posted in the forum, and these are the answers provided by the professor. So this is the primary reason why I say please post it in the forum also. If you are if you tend to forget uh, to ask during the live session, because if you post it in the forum, you can get answers from the professors, as well as we also try to reply through the forum or during the live session. So make the best use of the forum. Okay, don't hesitate to ask your question in the forum. Okay. So these were some of the interesting questions that were asked, and I have just shared it with you. So that's it with the session. So any other questions? Any other
Not
questions?
now because I don't have any questions.
Okay.
Yeah, I got. It's very informative
Okay.
because I got too many informative things. Yeah.
Okay. Okay. Good. Good. Please make use of the forum. Go through the lectures and ask your question in the live session. as well as in the try to make use of the forum to the best possible extent. As you can see that the questions that were posted in the forum, they were answered also. Okay, so make the best use of the forum as well as the live sessions. Okay, and go through the lectures. Okay.
Uh, Now the week 4 is going.
Yes, week 4 you have the assignments alive.
Yeah,
The lectures are there, and you have the assignments also. I think your assignment deadline is on Wednesday.
yeah, this Wednesday. Yeah, you,
Yes, yes,
week
yes.
5 is also good.
Yes, we
Totally, no, I don't know because how many weeks we have
12
totally now?
week
The
12
four
weeks you
12
will
weeks.
have. 12
Okay.
weeks. Yes, 12 weeks you will have. Lecture content for 12 weeks and the assignments for 12 weeks you will have. Okay?
Okay. Okay. Got it.
Okay. Any other questions?
No, ma'am. Thank you.
Okay.
No, it's okay. No, it's okay. It's good. Okay. Okay. Thank you. Thank you.
Thank
Thank
you.
you very much.
Thank you. Have a happy weekend.
Yeah. Same to you.
Yeah,
Thank
ma'am.
you.
Thank you. Thank you.
Thank you.